Bismillahirrahmanirrahim. Good afternoon. Assalamualaikum to all of you. This is an introduction slide for the Advanced Process Control course KIL for 006 given by me in this semester. As you can see, the studies have shown that 40% of process loops at the moment are underperforming in the real world. Millions of dollars are lost due to this process variability and non-optimal control performance. Hence, advanced control are needed to reduce this variability and increase the quality throughput, and also to locate the hidden variability and underperforming loops, and also to get more precise control and reduce the energy consumption and improve sustainability of the process. Using conventional, you may get a lot of variations or oscillations. Using advanced, you reduce these oscillations, and with that you can move towards the limits or the control points and increase the profit of the system. So reduced variation allow operation closer to the limit, and in most cases towards the optimal operating point and better profit. In other words, you can go right to the limits of the operation from the normal conventional, where you're far away from the limit, go close to the limit, and that. In terms of definition, advanced control defined as an algorithm or strategy that differed from the PID controller, and most of it is associated with computer-based technology. Different definitions from academic industries, but in reality, in comprehensive definition would be that a controller or control strategy that differ from the conventional PID or differ in terms of the control strategy or the 4 elements loop that we see in PID. Under advanced, you can have classical advanced methods such as the cascade and ratio that you have seen before in your process control class, the feed-forward method that I will teach you later. Also, we have the other methods which have nothing to do with the PID, other modern advanced control strategies that we will touch in this class. Under advanced, we have different strategies: the adaptive PID-based, the model-based, and the AI-based methods. The adaptive PID basically is a procedure of tuning the PID automatically using various methods. These are all well-established controllers and all commercialized in the real world, such as the Honeywell UDC320 controller, the Emerson Delta V5 Adapt controller, Foxborough Exact controller, the Yokogawa SLPC controller, the Spivak Psycho, and many other controllers in the market. Honeywell uses a small collection of transfer function with fuzzy logic to do the controller tuning. Emerson Delta 5 used the updated process models of each operating region to do the tuning. Foxborough uses error response curve with heuristic and pattern recognition to do the tuning, which you have seen in your lab. SLBC uses first order plus date time model to minimize the integral error and do the tuning, as you also seen in your lab. And the Spivak Psycho uses standard technique with fuzzy logic. Different methods, different controllers, and most of them are well established and already being implemented in the real world. It's already a hardware-based system or software-based system that is really well used in the real world. It's just a matter of different methods for tuning for the PID and doing online or automatic tuning. One is a model-based controllers. Divided into model predictive, the GLC, GMC, the sliding mode, and inverse model methods. The most widely used is the MPC, which started basically in 1970 by Shell Oil. It's the most advanced control technique used in the process industries, and in most industries, when they talk about advanced, they're talking about MPC, and majority is in refining and petrochemical, and also in chemical and pulp papers are also the other areas using this model predictive method. Models are using normally models developed to plant testing and can be used for multi-variable control as well. The framework is basically to optimize the output and the manipulated variable, which constrain on the manipulated for the manipulated variables, the lower, upper and lower, and also the change of the manipulated. So this is just a matter of optimizing the objective function and putting it into the controller loop. And normally done on the second level, on the supervisory level for advanced using MPC, instead of using the PID and so on for the second level, use the MPC. Can also be used on the lower level where directly control all the different types of controllers in the plant itself. But this is how normally it's implemented. Different types of MPC or different generation, but these are the normal common one now. The process perfector, the MC plus, Delta 5, 3D MPC, profit controller, pavilion 8, and these are controllers that you find in the value now used by Shell or Petronas. You may be familiar with gone to these industries, some of these controls that they're using for the advanced control method. The other one is the globally linearized, which is basically linearizing the process, non-linear process, with linearizing state feedback and then using linear controller to control the system once it's been linearized. This is the globally linearizing controller structure. The other is the GMC sliding mode or the inverse model controllers. We categorize them as model-based controller, and formulation is in this form: x dot fx plus g. There's a g here, so some g missing here, and u. So you design the u getting the manipulated variable in this form or in other forms. So different strategies give different form of the external input v. For the GMC, it is form closely similar to what you've seen in PID, but it's not the same. But the ideas are there. Using this V in this form, and finally the input, the manipulated variable is designed in this methodology. The other one is the AI based controllers, which is the latest types of controllers designed and used little bit by little bit. Basically, we have the neural network based controller, we have the neural network direct inverse, we have the neural network inverse model, we have the adaptive neural network inverse model controller types. On the fuzzy logic, you have the conventional or the adaptive fuzzy logic types, or the genetic algorithm based controller, another AI. The neural network based controller based on the nodes, input, middle, and output node method coming from the brain, where the nucleus from one to another communicate through this axon using this sort of structure. And this is the artificial one, this is the natural one. And one of the methods that can be used, the neural network direct inverse, where the inverse model of the plant. This is the plant, you inverse it, you get the controller, and this is the inverse model. The inverse model is directly the perfect controller. Can be done to modeling or to using neural network, which is easier in most cases. You can get a software for this sort of neural network method subject. This one we develop our own on Paragon and using Visual Basic. This is controller acting as the primary controller in a cascade structure. The slave controller is a PID. The neural network is the primary controller, either using the direct neural network, the inverse model neural network, or the adaptive neural network, where you adapt the neural network online. The other one is the fuzzy logic. We're using fuzzy logic rule base. If the temperature is hot, then valve is not hot, valve is open. If hot, then valve is normally half open, the normal operation. If very hot, then it starts to close. This is how the human thinks, and this is how the fuzzy logic structure is based on. The human thinking, not in terms of actual number. The controller in terms is made up of this structure, the fuzzy fire. You convert the normal data into fuzzy sets, and then you use the fuzzy base just now. If this happen, what happen? If this happen, what will you do? If this happen, what will you do? And then this defuzzify to convert it back to the actual data. We call it the Eclipse data goes into the plant. It works on the actual data, not on the fuzzy data, using the center of area or mean of maximum method. You have a software, you can use it for conventional or adaptive method for FSC. You develop a software, you can use the software in. And finally, you have the genetic based algorithm controller. Basically, it uses the biological base system of male chromosome or female chromosome to come up with a offspring of the best output. So you decide the fitness, how you want to optimize using what method, what equation, in this case temperature. Then you do the selection of chromosome, you cross over chromosome, mutate the chromosome, see whether it optimizes or not. It doesn't, you do it again iteratively. With theirs, you stop at that. So these are the genetic operators. You have to decide the parameters basically in your formulation of the genetic algorithm, whether you do it for for modeling or control.